Welcome! In this lecture I want to discuss how we can control the scattering force by a magnetic field, changing the atomic resonance frequency via the Zeeman effect. An important application is the Zeeman slowing of an atomic beam based on a combination of an inhomogeneous magnetic field with circularly polarized laser light. But before starting a more detailed discussion, let me summarize some basic textbook knowledge on spectral lines and the Zeeman effect. The strong optical dipole transition used for laser cooling of alkali atoms has a substructure which is easily resolved by laser spectroscopy. To understand this structure, we first have to consider the coupling of the electron spin to the orbital motion. This spin-orbit coupling is responsible for the splitting of the electronically excited p state into a state with total electronic angular momentum 1/2, the lower one, and 3/2, the upper one. The corresponding doublet of spectral lines is referred to as the D-line doublet. The first one representing the D1 line and the second one the D2 line. For sodium, taken as a typical example, this so-called fine structure splitting is about 1 per mil of the transition energy. For lighter atoms, lithium, it is much less, but for heavy atoms, cesium representing an extreme case, the splitting is much larger. The next step is the so-called hyperfine splitting, resulting from coupling of the electron motion, orbital motion and spin to the nuclear spin. Let us stay with sodium as our example. Here, for the only stable isotope, has a mass number of 23, we find a nuclear spin I equals 3/2, and the interaction splits the singlet ground state into two hyperfine states, one labeled F equals 1 and the other one labeled F equals 2. The p3/2 excited state splits into four hyperfine states, F prime equals 0, 1, 2 and 3. Ground state hyperfine splittings are typically found in the range of a few gigahertz, for sodium about 1.8 gigahertz. And hyperfine splittings of electronically excited states are on the order of a few 10 megahertz, which is still larger than the natural line width of the transition. The details depend on the specific isotope, but the general structure is always the same. Laser excitation well resolves the hyperfine structure and allows us to select specific lines. Now the question is, where do we find a transition suited for laser cooling? It is essential to select a cycling transition, which allows us to scatter many photons. That means hundreds of thousands or even millions. Remember your atomic physics course, there is a selection rule, which says that an optical dipole transition can change the quantum number for the total angular momentum of the atom by a maximum amount of 1. In other words, changes of F by more than 1 in a single interaction process are forbidden. Now assume that the sodium atom with I equals 3/2 is in the upper hyperfine ground state where F equals 2. Laser light excites this to the upper hyperfine level of the electronically excited state where F prime equals 3. From this state it can only decay back to F equals 2 and the whole cycle can be repeated many times. This cycling transition is our laser cooling transition. In practice, we note that there can be small leaks caused by off-resonant excitations to the F prime equals 1 and 2 excited hyperfine levels. The atom can then decay into F equals 1, and this so-called optical pumping effect interrupts the cycling process. This can be remedied by an additional repumping laser that brings the atoms back into F equals 2. We stay with our example of an alkali atom with nuclear spin I equals 3/2, which is the case for sodium with mass number 23, but also for the potassium isotopes K39 and K41, as well as for the rubidium-87 isotope, and we consider the laser cooling transition from F equals 2 to F prime equals 3. If the magnetic field is not too strong, the splitting can be described in terms of the linear Zeeman effect. In a magnetic field, a state with total angular momentum F splits into two f+1 different substates, with the magnetic quantum number mf going from -f to +f. This gives us 5 sublevels in the f equals 2 ground state and 7 sublevels in the f prime equals 3 excited state. If we now assume that the energy shifts caused by the magnetic field remain small as compared to the hyperfine splitting, then the Zeeman effect is linear with level shifts proportional to mf. This behavior is described by a simple formula for the energy shifts, which reads delta E equals mf times gf times mu b times b. Here mf is the magnetic quantum number we have already introduced. Gf is a so-called gyromagnetic factor which depends on the specific hyperfine level and which can be calculated from the angular momentum configuration as described in almost any atomic physics textbook. Mu b is Bohr's magneton, which is a constant of nature and in frequency units amounts to 1.4 MHz per Gauss. And finally, B is the magnetic field strength, which we can control in an experiment. Here please note that in the community of laser cooling and cold atom research, the unit Gauss is more common than the SI unit Tesla. Just for practical reasons. 1 Gauss corresponds to 10 to the -4 Tesla. For an alkali atom with nuclear spin of I equals 3/2, the gyromagnetic factor in the F equals 2 hyperfine ground state is GF equals 1/2. This means that the maximum possible energy shift realized with MFGF equals 1 amounts to the magnetic energy mu BB. This is useful to know in particular when dealing with magnetic trapping potentials, as we will discuss in another lecture later. In the F prime equals 3 electronically excited state, where the gyromagnetic factor is 2/3, the largest possible shifts appear for MF equals ±3 and amount to twice the magnetic energy, that is 2 mu BB. Note that GF can also be negative. Don't be surprised. This is the case, for example, for the lower hyperfine state with F equals 1, which is not shown in the figure on this slide. Let us now consider optical transitions between the Zeeman split ground state and excited state. Here we see so-called pi transitions. These are the transitions between states with the same value of the magnetic quantum number m. Here, the absorption or the emission of a photon does not change the orientation of the total angular momentum of the atom. The transition energies follow the simple expression shown here. If the gyromagnetic factor is the same for the ground state and the excited state, then there will be no line splitting to first order magnetic field. But in many cases, they are not the same. For our F equals 2 to F prime equals 3 transition in alkali atoms, the difference in G factors is 1/6. But now let us consider sigma plus transitions. Here the absorption of a photon changes the orientation of the total angular momentum of the atom, increasing the magnetic quantum number by 1. You can see in the figure that the arrows are now just a bit longer. The splitting of the transition frequency now follows this general formula with our specific G factor values here. Sigma minus transitions can be understood analogously with the magnetic quantum number changing by -1. Of particular interest are the sigma plus and minus transitions that connect states of maximum possible m. They are great cycling transitions for laser cooling. We have already discussed that from an excited state with F prime equals 3, an atom can only decay into F equals 2. But this is not a perfect solution because of off-resonant excitations and pumping processes to other hyperfine levels. With sigma light, as indicated here, we have an additional reason why the atoms cannot leave the cycling process. After excitation from the m equals +2 ground state to the m prime equals 3 excited state, by sigma plus light, it can only decay back into the m equals +2 Zeeman sublevel of the ground state because the maximum possible change of m is 1. The same is true for sigma minus light and negative m. This selection rule suppresses unwanted excitation processes very efficiently. This can be very important for real experiments. The Zeeman shift of these particular sigma transitions follows our formula here. The prefactor in square brackets depends on the particular g factors, but for our special case it is 1. The proportionality constant between the Zeeman shift of the optical transition and the magnetic field B is just Bohr's magneton μb. But for the sake of generality in the following considerations, I will simply call it mu. Good, we have discussed sigma plus, sigma minus and pi transitions. But what is the property of light that makes the difference? Yes, of course, it's the polarization that makes the difference. Is circularly polarized light really sigma light? And is linearly polarized light really pi light, as one often hears? What do you think? The answer is not that simple. In many cases it is indeed like that, but not always. Unfortunately, it is a frequent source of confusion and misconception, even in some textbooks and in the scientific literature. Therefore, I will try my best to make this crystal clear. Here you see an illustration of a circularly polarized laser beam. The electric field vector rotates around the laser beam, here as indicated by the right hand. We call it right-handed circular polarization. Now comes a very important point. To describe the situation properly in terms of sigma and pi light, we have to choose our quantization axis. Let us choose it along the laser beam, that is, along the k vector of the traveling electromagnetic wave. The electric field vector rotates around the quantization axis in a way that makes it sigma plus light. What if we choose the quantization axis in opposite direction, like this one? Physically, it is the same situation. Right-handed circular polarization. Nothing has changed. But now we have sigma minus light instead of sigma plus. This teaches us a very important lesson. The term handedness refers to the direction of propagation of a laser beam. But sigma plus and sigma minus refer to the chosen quantization axis. Let us now consider linearly polarized light. First of all, keep in mind that electromagnetic waves are transverse waves. The electric field vector E is always perpendicular to the wave vector k, the laser beam axis. I will now interpret this situation in 3 different ways, depending on the choice of the quantization axis. Here, the quantization axis is oriented along the laser beam axis. And here is the same configuration, but with the quantization axis parallel to the electric field and perpendicular to the beam axis. And here again the same configuration, but with the quantization axis perpendicular to the electric field and also perpendicular to the beam axis. 3 different ways to look at one and the same configuration. I call them cases 1, 2 and 3. In case 1, the linearly polarized wave can be interpreted as a coherent superposition of a sigma plus wave and a sigma minus wave, right-handed and left-handed. In case 2, with the quantization axis parallel to the electric field, we have pure pi light. There is no sigma component. In case 3, with the quantization axis perpendicular to the laser beam and to the electric field, we again have a situation of both sigma plus and sigma minus. But there is a fundamental difference in comparison with case 1. In case 1, one can in principle realize a kind of filter that absorbs the sigma plus and transmits the sigma minus light. This can be a cold atom cloud in a magnetic field. Or the object can cause a phase shift between the 2 circular components. The effect of different absorption corresponds to the so-called circular dichroism, and the relative phase shift is the origin of the Faraday effect, the rotation of the plane of linear polarization caused by a magnetic field. In case 3, whatever you do to one circular component, you will have the same effect on the other one. The two circular components are inseparable. This fundamental difference between situations 1 and 3 is very important if one takes absorption images of cold atom clouds in a magnetic field, as we have experienced many times in our laboratories. One and the same situation interpreted in 3 different ways. The particular choice of the quantization axis makes the difference. This brings us to the interesting question how to choose the quantization axis to describe a specific problem. The general answer is consider the problem in the most intuitive or convenient way. You have the freedom to do that. Let us have a look at a few examples of an atom placed into a magnetic field. The Zeeman effect will lead to a splitting of the levels, which we want to probe with a circularly polarized laser beam propagating along the magnetic field. With the quantization axis chosen parallel to B, the right-handed circular polarization corresponds to sigma plus, and it will drive sigma plus transitions in the atom. In a second example, we probe the atom with another beam which propagates perpendicular to B and which has linear polarization parallel to B. We choose our quantization axis along B and we find the polarization is pi. Accordingly, we drive pi transitions in the atom. Third example. Both the laser beam axis and the electric field are perpendicular to the B field, which we again choose as quantization axis. The light is now an inseparable combination of sigma plus and sigma minus, and we drive both sigma plus and sigma minus transitions in the atom. There are different ways to describe the physics of atoms in a magnetic field and irradiated by polarized laser light. I personally learned a lot about the various magneto-optical effects in their description during my diploma thesis work in the mid-1980s at the University of Hanover in Germany. Let us now move on to a conceptually quite simple case which is of great practical importance. The Zeeman slowing of atomic beams represents a beautiful example for the powerful control of the scattering force by magnetic fields. Let us start with a quick visit to our Newland laboratory, where we have set up in the last few years a quantum gas microscope for dysprosium atoms. We want to study the effect of exotic interactions in this quantum gas microscope. So you see the apparatus in an early stage where it was just a vacuum apparatus was assembled. Now it's covered everything with a lot of optics. And here you see in the center, you see the Zeeman slower. Here on a typical length of nearly half a meter, we slow the dysprosium atoms coming from an atomic beam oven down to low velocities where we can capture them then in the glass cell on the right hand side. Then further experiments are carried out in this glass cell, which also looks very beautiful. We have discussed the slowing of an atomic beam already in the lecture on the spontaneous scattering force and applications. Let me just remind you on the basic things. So the atomic beam has a typical Maxwell-Boltzmann velocity distribution, and at a temperature of the oven of 200 degrees Celsius for rubidium atoms, we have most probable velocity at about 300 meters per second, which is very typical for rubidium. This means that with a maximum possible scattering force, we need a minimum distance of 40 centimeters to slow down the beam, the atoms in the beam from 300 millimeters per second down to almost zero, so 40 centimeters. In practice, however, we never use this maximum force. It would be a very unstable situation. We'll discuss it later. So we have some safety margin. We call it the safety factor or safety parameter. So we only use, let's say, 50% of the maximum force, or maybe a little bit more. So with 50% of the maximum force, we get a typical slowing length of 80 centimeters. So because of the Doppler effect, so the scattering force only acts in a narrow velocity subclass, which is typically the width of this distribution divided by 100. And in this velocity distribution, it kind of produces a hole, decelerates the atoms downwards, and then they get out of resonance and they pile up in a narrow peak there. So the resonance condition is that the laser detuning from the atomic line so that means omega minus omega naught, that's the detuning, that should be equal to the Doppler shift kV. Then you have the resonance condition there where the hole is burnt here. So as I said, deceleration just takes place in a narrow velocity group of the saturation broadened natural line width. To achieve a high flux of cold atoms, we want to slow, in an ideal case, all atoms which are below the maximum, the most probable velocity, we want to slow them down to nearly zero. But this changes then during the slowing, the resonance condition changes. And there are two ways to achieve that. One is changing the laser frequency via the detuning, that's the so-called chirp method. And the other method, the one which is more efficient, is Zeeman slowing, where we change the resonance frequency via the Zeeman effect. And this goes back to the great idea of Zeeman slowing, making use of the Zeeman effect in an inhomogeneous magnetic field, as schematically shown here. Actually, this is a figure, that is an image which is taken from the original publication where this method was proposed in 1982. And a few years later, in 1985, even stopping of the atoms, not only deceleration, was demonstrated using this method. The Zeeman compensation of the Doppler shift depends on the position here. So the resonance condition varies with the position on the beam, unlike the chirp method where it's just frequency dependent. And this setup can really produce a continuous flux of slow atoms, which can be very efficient, for example, to load then other traps, and it has become a standard tool for many present experiments. You will see if you visit our labs, you can see many different Zeeman slower setups. It's used on almost all the experiments that we have. Now let's consider the Zeeman slowing in some more detail. And first of all, we assume that we have a constant deceleration A, which is the scattering force divided by the mass simply. That's the constant deceleration A, which is of course then below the maximum possible deceleration. And we start at an initial velocity v0 and want to slow down to zero, stop the atomic beam. So, and then just first year physics tells us that the velocity as a function of the position should be described by a square root type behavior. So this is a square root function. So the velocity is square root of 2 times a times L minus x, where L is the maximum slowing distance and x is the position, and we get this parabola type behavior. Let us look at typical numbers. For the rubidium example, we start at 300 meters per second and slow down to 0. Then we have already calculated we need about 80 centimeters to do this with the force of 5.6 times 10 to the 4 meters per second squared acceleration. Good. And now we are interested, the velocity change of the slowing process is from 300 meters per second to 0. That means 300 meters per second. And we calculate the corresponding Doppler shift. And this is for rubidium 385 megahertz. So these 385 megahertz we have to compensate by the Zeeman effect. Okay, now let's express what we see here in terms of magnetic fields. Then it looks like this. The Zeeman shift now would correspond to 275 Gauss. So the field has to change by 275 Gauss. and we have an initial field at x equals 0, this is when the atoms enter the slower, which can be set to B0. Actually B0 can be chosen freely. And then we need a 275 Gauss higher magnetic field, B0 plus delta B, at the entrance of the slower. And then we can show that the magnetic field has to change according to the expression given here. How to realize the corresponding Zeeman shift in practice in an experiment? Yeah, the original idea, which was also the basis of many experiments now, is to use a tapered solenoid, which produces a higher field at the entrance and then a decreasing field down to a field close to 0, where the atomic beam, the slow atomic beam, is then extracted. That was the original suggestion from the paper published in 1982. Now something very important. Zeeman slowing is not only about the force you need for this. Of course, you have to provide the force which is large enough. There's also the very important question of stability. Let me explain it here. Here you see the typical Lorentzian force profile for the case of kind of moderate saturation. Here you stay clearly with the force, the maximum force at the top of the Lorentzian curve, which is below the maximum force at full saturation. Okay, but now we consider a slowing force which is, according to the Zeeman-Storer design, half of the maximum force. So we introduce eta equals 0.5 in this case as the safety factor. And then we see that we have a certain point here where we have a force equilibrium, so the scattering force is large enough to provide the necessary deceleration. But now you see that you have something like a stable point. If you have a velocity which is below the stable velocity, then the slowing effect will be smaller than the design value, and so the atoms will reach the stable point. They will pushed in the velocity space to the stable point. The same if the velocity is a little bit higher than the velocity of the stable point, then there will be more deceleration and they will be pushed to the stable point. And then at the stable point we have a kind of friction. We can take the first order derivative and get a friction coefficient there. And we have discussed the effect of such a friction term already in connection with the optical molasses. There is some kind of cooling, a damping of the relative velocity towards the stable point. This is a very important point to make the slower work efficiently. Okay, but now we see that there is a limited capture range. So this slowing process can capture all the atoms below the stable point and a little bit, kind of typically 2 times the line width, larger than the stable point velocity. But if you have even higher velocity, then the slowing laser is so far out of resonance that the deceleration is no longer enough, and so the slowing force will then push the slower atoms down, but the atoms above this critical velocity is unstable and they cannot participate in the slowing process. So that's very important. You have this capture range and the unstable region, and you can define now the stable velocity as the velocity at the stable point, and you can define a maximum capture velocity here on the other side of the Lorentzian profile, which is typically 2 times the saturation broadened line width, larger than the stable point velocity. Details depending on the safety factor one has chosen. And here is a little simulation of the slowing process, which also shows the effect of the stable velocity and the capture range. The parameters are, as in the example before, it's rubidium 87 and slowed down with half of the maximum possible slowing force. The safety parameter is 0.5. I've assumed a saturation parameter of 10, and you see the atoms are stopped then on a distance of 80 centimeters, as we have already calculated before. The red curve here, that's the stable velocity, and this is the square root behavior we have discussed before. So atoms below, with a velocity below these 300 meters per second, they first don't see the slowing light, but then when traveling a little bit in the Zeeman slower at some certain distance, they reach resonance, and then they are affected by the laser light and slowed down, and they are actually cooled then towards this red line, this red curve, which means they keep now the stable velocity, and at the stable velocity they are brought down to zero velocity. That's the behavior in the stable region. If we are slightly above this initial velocity of 200 meters per second, so in this example 320 meters per second, then you see they are just captured. They have a velocity which is higher than the capture velocity, but it's still stable. So they are decelerated a little bit more, and then reach after a while here, after a little bit more than 10 centimeters, they reach the stable velocity and are decelerated as the other ones. But when we are above the maximum capture velocity, here for atoms starting with 340 meters per second, then they hardly see the light, the slower cannot affect them, they are not captured, and they simply move towards the slower when they have very little deceleration. So they are not used for the slowing, and they are lost in this process. And here is an intermediate summary on Zeeman slowing. Some more details will come a little bit later. Zeeman slowing requires an inhomogeneous magnetic field, which is usually created by a tapered solenoid. Here you see it on a photo taken from our lithium-potassium slowing and trapping machine, which is active in the Ikoki fermion lab. You clearly see in the center this conical solenoid, which provides the necessary field for Zeeman slowing. Zeeman slowing does not use the maximum force, but for stability reasons a bit less. Typically 50% of the maximum possible scattering force at full saturation, or a little bit more. There is a stable velocity, and atoms are cooled to this velocity, a damping of the relative motion in the moving frame. Then there is the maximum capture velocity. Atoms below this capture velocity take part in the slowing process, and they are cooled to the stable velocity. In between the stable and the maximum capture velocity, we have the resonant velocity, and that's important for the theory, because there we have the resonance condition fulfilled. And now we have to extend our Zeeman slowing theory a little bit. Before we have just argued with the resonant velocity for slowing, but we now know the stable velocity is relevant, which is a little bit below the resonant velocity. So we have to take a little shift into account. Okay, so the resonance detuning as seen by an atom in the Zeeman slower, delta, is given by the Doppler shifted laser frequency, omega plus kV, and the Zeeman shifted transition frequency minus omega naught plus mu over h bar times b. So we assume here a Zeeman shift corresponding to what we have discussed before, the transition between the m levels, the maximum m levels in an alkali atom. Then we can set mu equals mu b in this case. And we assume, as before, that slowing takes place as a constant deceleration a, and then we get for the velocity as a function of the position, we get the square root-like behavior. We now express the acceleration a in terms of the scattering force, including the resonance expression, and by solving for delta, we get this expression on the right hand side here. Delta equals minus gamma half times square root s over eta minus s minus 1. We finally arrive at this expression for the magnetic field as a function of the position x in the slower. It includes, via delta, the little shift between stable velocity and resonant velocity. It can be written in this simple way after introducing abbreviations B0 and delta B. It is very interesting to note that one has the free choice of the laser frequency omega. And this is free choice of the offset and magnetic field. That means the magnetic field has to be from entrance and exit of the slower, the difference has to be delta B. But the offset is in principle free. It can be negative, whereas B0 plus delta B is positive. And then one has a zero crossing of the magnetic field in the slower. And this brings me to three variations on how to build a Zeeman slower. The first one, that's the classical way to do it, a so-called decreasing field slower. Here you enter the slower at high magnetic field. large Zeeman effect, and with the pass through the solenoid, the magnetic field gets weaker and weaker. So when the atoms exit the slower, there are little effect from the magnetic field, residual magnetic field effects near the slower exit. This is the traditional way to do it. Second version is the so-called increasing field slower. So you enter the slower at low magnetic field and then its magnitude increases. Yeah, this really has an advantage, in particular when you operate then or you load weak optical traps, so weak, let's say magneto-optical traps on weak optical transitions, because the slowing light at the end of the slower is far detuned from the atomic resonance, a few hundred megahertz, so the destructive effect on the mod is very, very weak. And this is crucial if you want to load, for example, mods operated on intercombination lines. Good, the third one, this is the so-called spin flip slower. I will explain you in a minute why I don't like this expression. Okay, let me describe it. This enters at a kind of intermediate magnetic field, not too large, and then it goes to a zero crossing and then has opposite sign, acquires opposite sign. And this configuration combines advantages of the two above slowers, particularly that it kind of has weak effect then on the atoms in a mod which is loaded with such a slower. And it also has the advantage that the power consumption is in total much less. So you have less power consumption, you have less heating on your optical table, you have less destructive effects. That's really an advantage. But now I have to tell you why I don't like this expression spin flip slower. Earlier in the lecture we discussed the polarization of the laser and the role of the quantization axis. So what is sigma plus, what is sigma minus, what is sigma right hand, what is left hand circular polarization. Okay, let us consider such a so-called spin flip slower. We enter, so the first tapered solenoid, at the entrance we have high magnetic field, and then the magnetic field gets smaller, and then it changes its direction. And then the magnetic field increases again, the modulus of the magnetic field increases again. Okay, now we assume that we use right-hand circularly polarized light, and we choose a quantization axis as shown here, a global quantization axis, where sigma right hand corresponds to sigma plus light. Okay, fine. Now, actually I don't see any spin flip here, so I have right hand circular polarization, stays right hand circular polarization. I have a global quantization axis in the shown direction, and sigma plus light stays sigma plus light. But now I can alternatively, I can think I'm clever, and I choose the local quantization axis parallel to the B field in the first slower and the second slower section, so that means with opposite sign. With this joint, okay, one part of the slower is operated with sigma minus light, the other one with sigma plus light. But is this a spin flip? When the spin flips relative to the quantization axis, and since the quantization axis is flipped, those are the spin flips. But there's no spin flip. So this term spin flip slower is really a misnomer, to my honest opinion. I don't like it very much, but people often use it in the lab. I don't have a better suggestion. But my recommendation in general, if you deal with polarization and different quantization axes, stay with your global choice. Unless there's really strong reason for changing it, stay with your choice of the quantization axis and interpret the whole physical problem with this global quantization axis. Local quantization axis can be sometimes useful, but this can also lead to confusion. There is no spin flip in a spin flip slower. This highlights this very clearly. Finally, let me show you the design of a real Zeeman slower, which consists of several segments of coils here in the setup. That's from the Newland experiment, or quantum gas microscope for dysprosium atoms. And you clearly see these so-called spin flip slower, decreasing field section and an increasing field section, and there's zero magnetic field somewhere in between, and this way a magneto-optical trap is loaded. And by designing all the different coils, the different segments in a proper way, and running carefully the right currents through this, you get a profile. This is the orange line here, which really resembles this square root-like behavior needed for the Zeeman slower. And you see also there's a zero crossing and there's an extraction where the field is relatively high, but this can be a big advantage when you don't want to destroy your magneto-optical trap in this process. Okay, finally, let's have a look into the laboratory again. You've seen this already. I've discussed it already at the very beginning. Now, I mean, it's full of optics and producing results, but the Zeeman slower is a very important element in this setup. And as a last slide, I want to show this one here. And this is actually from a recent master thesis performed in our group. And here the electromagnetic field slower, that is standard. I mean, most of the groups work with electromagnets, was replaced by a permanent magnet setup. And the big advantage is that this does not heat up because of power dissipation in the currents. So if you want to have a very stable setup on your optical table, that is very important. And you have a fixed setup, you don't consume power, you don't heat up the setup, and this is compact and can be very stable. And I'm confident that this will be a very interesting development for our future experiments. So with that, I want to thank you for your attention.